Hello everybody, it's me Yasser again. Today I'm going to explain case study 2, which is about risk analysis. We're going to deal with the same dataset we used before, the Kokomo and NASA projects. And I believe at this point you already have this dataset installed or imported in Excel file. So you shouldn't have any problem dealing with the data in Excel file. But what we need today is going through the requirement of the assignments and highlighting some of the references here or some of the extra reading that you need to do, and also go to this quick presentations to just explain a little bit about risk analysis and some of the concepts like some of the source of uncertainty and an example of decision tree, the algorithm that we suggest to use it for your risk analysis. And lastly, we're going to show or demonstrate the implementation of the regression tree or decision tree in R. Before talking about these steps, we need just to explain briefly what is R and how to install it, and then we go to the explain some of the or how to implement the decision tree algorithm on R. So let's begin. So first you are required in this study to first you need to define your metrics. So you have two kind of metrics. You have the input metrics, or it is also in some books they refer to this input as independent metrics or independent variables. In our case, it's going to be the cost drivers, which is the 15 metrics that we used uh, in the Kokomo model as a multipliers, or to calculate the multipliers. So we have these 15 metrics starting from the reliability, data, complex, etc. And the outcome metric here is going to be the actual effort. And as you know, actual effort is reported in continuous format. Uh, it has numbers 10, 20, 100, and so on. So we need to talk a little bit about how to form or reformat this by inventing or by creating another metric. And this metric you could give it a name, for example, like for estimated status, or you can give it any other name to just help you to recognize uh, the the job of this variable or what this variable is about. So the outcome metric is, as we mentioned, that it's continuous variable, so we need to convert it to classes. So what classes we have three. We can. I mean, this is your choice. You have three classes, or you can get two classes only. So if you, in case you have three classes, then you need to find projects that are overestimated or underestimated or has the exact estimation. Exact estimation, that means the estimated variable is equal exactly as the actual estimation. So the estimation or the estimated effort is equal to the actual effort. And as you know from the previous case study, this is not possible because all uh, all projects are not identical, in terms of the two variables of the actual and the estimated efforts. So for that reason, we create a margin, or we suggest use a 20% margin. So any project below or above 20%, then we can call it, for example, if it is overestimated 19%, then this we can consider it as exact estimation, and we can give it a code. This code can be, for example, 0, or that mean exact estimation. So we inject this 0 for every project that has actual and estimated efforts are below 20%. There is no gap between them more than, the maximum gap between them is 20%. So if it is over 20%, that's mean it is overestimated, and we can give it another code like 1, okay? And if it is 20% or less than 20%, so minus 20%, then it can be considered as we can give it like minus 1 code. So we have three factors here. We have 0, minus 1, 1. In case if you want to do two classes, you can do it like 0, 1 only, okay? So you have the accurate estimation, and this is also the same case, 20%. I'm going to explain why 20%, okay? So 20%, you can choose 10%, you can choose 25%, but it has to be like in this range, because we I mean we want to build a model that can at least we can have less than 20% error in the estimation, or we can measure how or the we can measure, for example, the error in the estimation within the 20%. So we don't want to go more than that, So this is also bad estimation. We can call this accurate estimation or and bad estimation. So we can give this, for example, 1. We can, for example, treat this 1, and when it is bad estimation, we give it the code 0. So good estimation is 1, bad estimation is 0. So this is like two options. You can go with this or with that. So you just need to change the format to factor, and we're going to explain how to do that in R. So we have number 3. There is no requirement here, but just like a notice that, or a remark, that you need to or input metrics can be categorical, can be left in or can be used in categorical format. Then 4, you need to implement in R or in any other tools you are familiar with. If you're not familiar with any, then you can watch this video to see my demonstration in R, and you can try to implement it yourself. So the implementation here is we need to use the tree regression to build decision tree, and lastly we need to produce the final results of the model and the decision tree plot, which should be something like this. The tree you are producing is something like that. We coming to this, okay? So this is the requirement actually, and this is extra reading in case you want to understand the risk analysis, because risk analysis is very big topics, and it can apply in any field or in any field of engineering. But these 3 papers discuss the risk analysis specifically in software engineering and more in effort. Uh, so let's go to the presentation here very quickly. So we need to understand that we have two kind of risk analysis. There is qualitative and there is quantitative. So in the qualitative, we use scale, for example, like low, medium, high. Uh, Something like this here. Uh, but this is actually not low, medium, and high. This is like this is maybe I wouldn't consider this as a scale. I will the other option is quantitative. Quantitative is to calculate the probability of each risk. So this is actually what we want to find. So for example, the risk we have is over and underestimate. This is the two risks that we don't want. So exact estimation is okay, it's not risk. This is the good option. Okay, this is the for example, and in this case also, this is the accurate estimation, or the good estimation is the good option that we want. I mean, we want to see our model that when we calculate the probability, we see the highest probability is going towards these two, this one or this one. So if the probability is going to here or there, then the model is having or there is a problem in the model, and you need to understand what's caused this problem, or what metrics are causing these issues. So that's why we inject, or we put the cost driver metrics, because we want to see which metrics are driving the model, or driving the to have a bad estimation. You can read more using this link here. Okay, this is also from one of the reference I provided earlier. So in this one there is also 10 project, and this is the actual effort, and this is what is called the residual, or the residual, and this is calculated by the subtracting the estimate from the actual. So it gives, for example, minus. When it gives minus, that's mean the actual is lower than the estimate, and it gives positive, which means overestimate. So if you notice here, that's either over or underestimate. But if you take, for example, here, this is 20 hours higher than the actual. I mean, there is a 20. Okay, there is 20%. So if you divide 20 by 220, then you get the percentage of deviation that this the estimate the deviation of the estimation, how is deviated from the actual. So 20 divided by 220, I believe it's close to 10%. So that means this can be considered as exact estimation. So project number 6 has good estimation. Okay. Same thing here is minus 17. It's very low value. So when you divide this, we get also something close to 8% or so. But for example, when we go here, we find minus 80. So this one is very bad estimation, because the actual is 115. So when you have minus 85 underestimation, then you are very far from the actual. So that's one is very bad estimation. And so in your model, so you need to calculate this one. So actually, to get the percentage, okay, you can get the absolute value. So when you get the absolute value, you get all these positive, and then you divide it by the actual effort, and you will get the deviation of the estimate, how the estimate is deviated from the actual. But this is in case if you want to have two classes. You will have like a percentage, how the estimate is deviated, so it is give you a number like 0.2, that's mean 20%, or 0.21, or more or less. So but if you want to find the underestimated, and you want to use three classes, then you don't take the absolute value, you leave it like you just subtract this one from this one, and then you can divide by the actual effort, and then you get, so when it is minus, that's mean it is underestimated, or when it is positive, that means overestimated. Okay, second thing, this one I think I mentioned, we talked earlier, that overestimation and underestimation is to risk, why? Because overestimation, when you put too much cost on the project, okay, some maybe say that, okay, this is good, at least we didn't lose, but this is bad, because when you want to get a deal with a company, and you have estimated their projects very high, then you're not gonna get the project. They put you down. So this option is also bad. Is as bad as underestimation. So underestimation is also bad, because if you underestimate, that means you are losing in that project. So you are paying more than what you're getting from that project. So if this, okay, this might happen for one or two projects, but you can fix it with other projects. But if this keep happening to very often, then you you going to be, the company going to be goes to bankrupt, and maybe close down. So why 20%? Because if you see this figure, this is actually the reference of this one is from the software engineering. It is the same reference I gave to you for the case study one. This is here show you how the estimation is close to the accurate. For example, this is the exact, the actual, this is the actual effort, okay? It's X, okay? Um, and here, if the estimation deviating, I mean, if it is over or underestimated. So this is show you how it's deviated from the actual cost based on the phase of the project. So at the early stages of the project, if you estimate at this point, it's very likely that you get like a very high deviation from the actual cost. But if you come to this point where the detailed design specification is understood by the programmer, they understood the specification, and the most accurate is when during the testing, I mean after development and during the testing. So here where you get the exact estimation, but obviously you are usually the estimation it's happen at some area here, but the more you come to the design of the program, the closest you come to the accurate estimation. So let's say, for example, here, so that's why it's very important that your guys or your programmers, they understood the specification. To understand the specification, it has to be uh, uh, involving also the customer, or the people who you are developing this program for. So this is actually, so 20% is actually because this is almost close to between these, I mean these 2 points here. When the program, so if we assume, for example, we are estimating at this level, so before we start the development, but at least at this point we understand the programmers that they understood all the specifications. So when they have that, so that's why we may consider this as the so any estimation between these 2 points, we can consider it exact estimation or good estimation. Let's say to be more accurate in choosing the words. Uh, let's call it good estimation. So now we move to understand the source of uncertainty when you have projects or when you have, this is actually another synonymous or another term of risk. So when you are uncertain of the of the cost of the project, so what's the source of that? What's the problem? So there is two source of that. So there is something called model error. So so how the model can, the error can be high in the model when not all factors included, and this is because some factors might be or might not be involved in the model or difficult to measure. So that's why they are not involved in the model. So this will reduce the accuracy of the model and increase the error. And also the measurement error. So when, for example, some of the input like inherent accuracy limitation or accuracy problem, like for example the function points or the size. So this is one way to calculate the size of the project. So when it's this it is called function point, it's already have accuracy limitation. Then this also produce limitation to or produce risk to the estimation also, and also the error in the assumption. So if you remember the cost drivers, the complexity and the reliability was having scales, right? Very high, extra high, very low, extra low. So these can be mistakenly assumed. I mean, it can be, for example, you assume that complexity is very high when it should be high only, not very high. So when you have it very high, then the estimation is going to be high, okay, as a result of that. But when you put it in the right, when you make the right assumption, then you will get the accurate, the more accurate results. This is a table also using this reference. So it's here. It show you some of the risk item. But what we need here to understand is something related to the software design, like and what's the risk management technique. Okay, this is out actually of our scope, but this is like the risk item, and or what's the risk, for example, like this is actually our what I was looking for actually. This realistic schedules and budgets. So we are, because this is our main goal, is to calculate the effort. So for that, so the solution for that, or the technique we need to use, is to have a detailed multi-source cost and the schedule estimation. So you need to have a good estimation here, and also there is other suggestions here, but we want to focus on the estimation. So we want to have a good estimation for that. So let's jump to here, and this one is just explain how the probability is changed when the size of the project is changed. For example, we have some of the cost drivers. There are multiple items or multiple metrics here, but if we focus only in the size, then we can see the probabilities here are increase with the increase of the size. So for example, with the small project, the probability that there is a failure in the cost, it will be very low, between 0 to 0.3, and it's medium when it is the project is medium, and it is high when the project is high. So at the end, this is an example of how to use the decision tree to calculate the risk. So this is an example to see how the income, or what's the metrics here are the risk to be the debt risk, so based on the income. So when you have, for example, when you are from 0 to 15, you are in high risk of being having debt. So when it is between 15 to 35k, for example, then you have there is another factor here, which is the credit history. If you are in debt, then it is very high risk or moderate risk. So when it is also bad credit history, your risk is very high for to have a problem in your income here, or to have a problem in your credit. And also when you are good at good credit history, then the risk is moderate. And when over 35, the story here is different. So for the unknown credit history is low risk, and with the good credit history. So this is actually what it shows here. So what we need here is we need to see effort in this as a root of the tree, and under the effort we see some of the metrics that having and from this metric, from every metric we see a branch of other, for example, metric that affecting this metric, and so on. So we want to see the direct effect and indirect effect. So we're going to have a tree similar to this one. So let's move on to explain shortly about R. So what is R? R is a statistical programming language similar to MATLAB and many other tools. It can run, it has the library of R. It contains a large amount of functions and algorithms and machine learning tools. We can implement any type or different kind of models, and we can plot some of the regression or the regression tree, and we can we can do a lot of statistical or mathematical calculation, or so it's very powerful tool. And the advantage, the highest advantage of R is that it's free source, and it's free to download, it's free to use. Some other tools are not free, like MATLAB is you need to be licensed to use it. So how to install it? We go to basically to RStudio, and then we go to download center, and from there we select. There is also some version that can cost you, but there is also the open source, or the free version, which basically what you need. So we just need the free one, the free version, and we can just hit the download, and then we find here the options. So select the one is fit on your system. This is to use it for Windows or Mac or Ubuntu or Fedora. So select the one you want, and then just simply download it, and it's very easy to download. I have it already installed in my computer, so I don't need to reinstall it again. So here we basically when we have so this is the main window, and these are some extra or help tools. I actually just need to import my dataset, and I have options here, I can go CSV or Excel. So let's try Excel here. See, preparing the data to. Sometimes importing Excel doesn't work here with R, so therefore it's better maybe to just install in CSV format. So for that I need to prepare my data. So this is case study 2, and so this is actually the Excel and this is the CSV. So it's very easy. So you need to open if you don't have the CSV, then you need to open the Excel and you need to save as, and you select CSV, and that's it. Save it. So it's already been saved CSV, so I don't need to overwrite it. So it's already saved here. I go again with R. So yeah, see, there is a problem to download using it's installing some packages. Okay, it seems work. I think this is importing Excel. Let's try. So let's try to import Excel. Okay, it's fine, I think. Yeah, it can import Excel. So yeah, either Excel or CSV, both are fine. So we just make sure that the first row has names, and that's it, and then we import. So we have the under this name Kokomo. So we can see summary of the Kokomo. So this is summary. So it show you all the metrics. So the first one is actually the project ID. So don't worry too much about this one. So this is the project name, application, and blah blah blah. And this is the other project other data. Remember, we create reliability 2 and data 2, complexity 2 to just because these are in categorical format and these are numerical format. So but what we need now is to create another so we have the estimated effort and we have the actual effort. So what we need to calculate the deviation percentage. So for example, we can call this metric as residual, or we can call it deviation. We can call it deviation, for example. So we can, okay, but before that we need to, okay, so we need to put the name of the data set, and we need to put the dollar sign, and then we put the name of the metric that we want to create, deviation, and here we can also put the Kokomo. So we want the deviations to be the actual effort minus the actual effort minus the we need to put the name of the data set at every time, and then dollar sign and the metric name or the metric name. So we need to put the estimated effort. So if we see now the Kokomo, and we now find a new, so if we go to summary Kokomo, so we can see now a new metric here. So the new metric here show you, so we have, this is the minimum and this is the maximum. So these are all from here to here is the almost the underestimation, and this part here is the overestimated, and here close to the median are the values that have good estimation. So we need to know how the deviation, we can create also another metric, we call it deviation 2. Oops, no, Kokomo. Deviation 2, and this is going to be equal to Kokomo deviation by Kokomo again actual effort. So let's do summary. We see in this here, so deviation 2, we can see that it gave me now a number. For example, let's see all the number here. So Kokomo deviation 2, so we can see here all the numbers that, so this is 0.32. So when it is 0.32, that means this one is 32% overestimated. When it is minus, that means underestimated. But by how much here? This one is 1.99. So this one is like 200% underestimated. So this one is underestimated. Here is, this one is one of the most accurate estimation, because this one is like 0.0001. So this one is like less than 1%. So this one is very good estimation, and this one also. This one is 0.007. This one close to 1%. Okay, so this one I can code this one as 0 and 1. I can work in this one in Excel and then import it again. I mean, for example, so it's easier maybe to do that calculation in Excel. So I can say deviation here will be equal actual minus estimation. I put these two between, sorry. So I put these two number in brackets and then divide them by actual again, and I will get here. So it's more clear here in Excel. So if you see here, and I can do something different. I can go to format cells. I mean, just to make sure that, and they take percentage. So decimal places I can leave it like 2 or 0, it doesn't matter. So this is show you by percentage here. So these are minus 1.7%, 2%, so these are good estimation, good estimation, good estimation, until here. So this one is no, minus 27%. So this is, I can put this one, I code it -1, and this one 32% overestimated, I code it 1, and so on. So I can go by that manually, or I can create here if statement. I say, for example, if the percentage is between this and that, then make this to be 0. If it is above 20%, then make it 1. If it is less than 20%, then make it -1. Like this one is very huge, big gap between the actual, or big deviation between actual and estimated, or the estimation between the actual effort and the estimated effort. So this one is going to be -1. So you can continue, carry on with this until you finish. So after you finish, okay, to not waste your time, I'm going to pause the video and finish this, and then come back again to continue recording. Okay, so we continue here. So I already created the if statement here. So it's actually, we have 0 good estimation, we have -1 bad estimation, and we have 1 also another a bad estimation. So now we need to move this file to, we save it first, and then we move it again to we import it again. So we import, is it no, it's text, so I need import Excel, so because I save it in Excel. So oops, yeah. Okay, so we make sure that the new metric are exist, so deviation 0, deviation 2, so this is our metric. So import. So we have now the Kokomo here, and now what we need to do is we need to do something very important, which is converting from numerical to categorical, because the deviation 2 is -1 or 0 or 1. We want that to be considered as a factorial. So in this case we need to change it. We go Kokomo and deviation 2. This is going to equal, we put this command as factor, so that means is consider this as a factor, and we put the this one again, the deviation 2. So that's mean take this one, or take this one, sorry, this metric, and save it as a factor in this, in here. So it's going to be the same. Deviation 2 is going to be converted from numerical to factorial using this function. So when we go this and we go by we summary, we take the summary of the Kokomo, we find here the deviation is converted. So it used to be deviation 2, it used to be this format, so it is changed now to be -1 we have 77 observation, and 0 we have 8 observation or 8 projects, and 1 we have 8 projects. So after we finish with that, we need now to build the model. So the model we need to use is it's called repart, or is the regression tree model. So we need to install the package. So we type install package, and then we put the quotation mark, and then inside it we type repart, and then we click. It will take a very short time, shouldn't take very long. Okay, I have a problem with connection here, so I need to try to fix it. Okay, I'll pause this video to fix the issue and then come again to continue. So yeah, it's working now actually, but takes a little while to finish. It usually takes less than that. Oops, it's failed again. Okay, let me solve it, and then I come again. Okay guys, I'm back, and the issue is fixed. So we don't need actually to install packages, because the package is already installed. But what we need is to include the library which contain those packages, or the function, or so we have the repart. We need to put the command library repart, and then we put another command library repart dot plot. So make sure just to put these two function, and the library will be installed in your R. So then you can build your model. So the model is easily, you give it first name, model 1 you can call it, and then you put this, and then you include the repart function, and here where you need to put the formula, it's very easy. So you need just to put the formula and comma and then the data, where the data is from. So my formula is like y equal x1 plus x2 plus x3. So let me write it down here. So this is my formula, equal y equal x1 plus x2 plus x3 blah 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 blah. So y here is the actual or the outcome, they call it the response variable or the outcome variable. So in my case it's going to be here either the three classes I created, the 1 minus 1, and I changed those to factorial. So this is going to be, which I call it deviation 2. So this is going to be my outcome, and then my metric here is the cost driver metrics. So it's going to be all the metric, reliability, data, complexity, and so on. So it's going to be like 15 metrics. So how to write down that? So you need to first start with the name of the dataset, which is Kokomo, and then you put the $sign, and then you can go scroll down until you see the metric you would like to choose, or you can write it down. So if I put D, then it's go direct to the metric start with D, then deviate. So DE is bring me to the deviation. So I need to put deviation 2, and then I cannot put equal here. What I put, or I substitute that by using the tilde sign, which is equivalent to equal, and then again I write the Kokomo dataset. That's mean use the metric inside this dataset. So which metric is going to be first? Reliability, and then plus Kokomo $sign, and then after reliability, what I have here, I don't need to add reliability 2, just enough reliability, the main metric. So I can put data plus, and I can go for all the other metrics, all the other 15 metrics, and then I put at the end I put comma, and then I type data equal, which is mean this model should call when I run the model, it should take the data from which dataset? From Kokomo. So I need to put this here, and that's it. So this is going to be my model. So after I finish all the metrics and then I press enter, so I have model 1. So I can type model 1 to just see what's the result, or what's my outcome here. So the outcome here is show you that a small tree, it has one branch only. So this is the root, okay, and this is if some of the metric is not included, that mean they are not they haven't significantly cause any risk. So that's mean the only risk is coming from the reliability. So we have the reliability when it is high or low or nominal, and we have another branch reliability when it is only very high. So we have this two branch low. So let's visualize that. So how to plot it? We can write down repart dot plot, and then type the name of the model, model 1. So this is our outcome. So we can zoom out that to see my tree. So when it is yes, when reliability is high, low, nominal, then it goes mean. So 89% of the data or of the effort is when the reliability under this classification. So they are actually -1. I mean, the underestimation is caused by the so here I have like because I have 3 classes, so at the end I end up, so it seems that exact estimation doesn't have any uh, is not significant here, because I have 89% when it is underestimated only when reliability is equal to these categories, and it's only 11% overestimated, okay, when uh, reliability is very high. Okay, so I can extend with that model. I mean, I can increase the metrics in the model. I go back to model 1 and I add more metric to see how this can change. So after this I add complexity, and I can add another metric. I should include them all to see, and the time. So okay, I increase 2 other metrics, and again I need to see the outcome of this. So when we come here, we see the complexity is even come here, complexity and time is actually more significant to have complexity and time than reliability or data. So we want also to visualize that, so we repart dot plot model 1. So this is okay, this is a different picture now. So we have here complexity when it is high or low or nominal. If it is yes, then so the highest portion actually, which is causing the underestimation, is actually when the complexity here. So if it is yes, then 76% of the projects that are underestimated are having complexity, this categories of complexity, and then the rest of the 24% of the project having overestimation. And who affecting here, or who having, or who which one is causing the effect here is the time when it is high or nominal. So when the time constraint is high or nominal, so it's overestimated, 14% overestimated, or either 10% underestimation. So this is actually how to write the model, how to report the results, how to understand, how to plot the result, and how to explain it. Read more about the regression model, and maybe if you go to the some of the tutorials talking about the decision tree, it maybe have some more explanation, maybe better than what I'm doing now, about how to explain the results and what does the result mean. Okay, so what's the numbers, these numbers means. Okay, so usually these numbers are the probabilities, or the, for example, like here is 0.83, so we have like 3 values, because we have 3 outcomes. We have 3 possible outcomes. So we have it's either -1 or 1 or 0. So if we build more metrics, we can see maybe different results. We can see more metrics here included or more outcome. So try to maybe understand more about the risk analysis topic, and the implementation is not very hard. The main point here is how to interpret the result and how to explain it. So I wish you very good luck. So if you have any questions, feel free to ask and I will try my best to answer them. Again, this is my email address. You are welcome to send me anytime. Thank you.